All right, so this is an explanation of the answer to the Dijkstra algorithm question. So let's go from the beginning. So the first thing we need to do is to establish all the edges. And that's fairly easy to do because the for each loop inside a while would look at all the incoming edges, and the incoming edges are relative to the vertex v. So after we picked v, the for each loop is going to look at all the potential edges. So so we have and also we know N8 and N3 are both destinations because they are in the set of Q initially. So in the graph, ah, okay, I got one step too far. There we go. So we know these two are destinations, and then we just add um, the edges as we go along. So every time we see in the log there's an edge, blah blah, we just kind of say, okay, there's an edge right there. So as a summary, okay, so we have a summary of all the edges here. So this is the first step, is to draw a picture of this. So we have N3 going to N8. We have um, N7 going to N3. And then we have N7 going to N8 directly. And then we have let's see what else goes to N8. N6 goes to N8. And then N7 goes to N8, which we took care of already. N7 goes to N8. So let's check out N2. All right, so N2 goes to N0, and N0 goes to N1. So N0 goes to N1. So I'm drawing the picture, on the side, and then N2 goes to N0. N2 also goes to N6. N6 goes to N8. Okay, we got that. N2 goes to N6. Okay, N0 goes to N1. I'm just double checking, reading from the bottom up. N2 goes to N0. N5 goes to N1. Okay, so N5 goes to N1. N3 goes to N5. N7 goes to N8. We got that. N7 goes to N2. Like so. And then N3 goes to N8. Okay, so we got everything. So the resulting graph is right here. Okay, so I know it looks kind of convoluted. All right, so the next thing we need to do is to find out how the paths, or the length of paths are compared to each other. So that part is summarized by a whole bunch of comparisons, and these constraints were built up as we update things, um, and also based on the ordering of how we choose which vertex to choose out of Q. So that's a summary of all of the lengths of paths between vertices. So we can see how the length of N3 and 8 is the smallest. Because N3 and the length of N3 and 8 does not appear on the left-hand side. So we know it is the absolute smallest, which means we can give it any particular value, and it should be okay. So we give N3 and 8 a particular value. So we can always start with something that is not too small, so that we later on, if we need to, we can make it smaller. So we'll start with a 3. And then we try to determine what do we know about the other ones. So anything that only appears on the right hand side are good starting points. um, so we can see how n1 n0 n1 is not only on the right hand side because it is greater than or equal to n3 and 8. Um, and we can also see how n5 and 1 is both on the left hand side here and also on the right hand side here. So it is kind of in between. All right. But we also want to see if n5 and 1 is greater than or equal to anything else. So we see that it is also greater than or equal to the length of n0 and 1, and then n0 and 1 is greater than or equal to the length of n3 and 8. And now the question is, are there any further constraints for n0 and 1? Does it appear on the left-hand side? And the answer is no, it does not. So we can determine this next. n0 and 1 has to be greater than or equal to the distance of n3 to n8. So we'll make this a 4 and go back to the graph. This is what we just, the other value that we have put into the graph. All right, so now we got those two taken care of. So it's helpful to replace what we already know as a constant, just so that it's easier to see from uh, the perspective of numerical values. So we already know that it's supposed to be 3, and this is supposed to be 4. And this is supposed to be 4, which is fine because 4 is greater than or equal to 3 is known. Okay. And that's all we have at this point. So now we try to determine what else do we know. We know the length of n5 to n1 is greater than or equal to 3, but it is also greater than or equal to 4. So this rule or this constraint is redundant. It is not really needed. And then we try to see what else do we know about the distance from n5 to n1. Particularly, we want to see how it appears on the left-hand side, and this is how it appears on the left-hand side. So we may not be able to determine that just yet. So there's the length of n6 to n8, and we know that n6 to n8 has to be greater than or equal to 3, and we want to see it has to be greater than or equal to 4, so it can be 5. And that's all we need to know about it, or that's all the constraints about it. So we know that n6 to n8 can be 5. So n6 to n8 is a 5, and pictorially speaking, this is what I have just added here. And now we replace all of those with a 5. Now I can use okay, since this is VI, I can do this. So I can say line 109 to line 120, uh, replace the length of n6 to n8 with 5 as a constant. And there we go. Okay, I think we missed some of them because this one is not removed. So let me manually change that. I think I probably specified the wrong number, the wrong line number. So this is a 5. This is also a 5. And there we go, 5, 5, and 5. There we go. All right. So now we need to look at the next smallest thing, which is probably n5, n1, because we see n5, n1 appearing here, but we also know that it has to be greater than or equal to 5, but it is less than or equal to n7, n3, n8, it is less than or equal to n2, n6, n8. Okay, so now we can say, okay, it only has to be greater than or equal to 4. So which means it can be 4, it can be 5. So we'll go ahead and see if 5 will work out. So let's switch back to the graph. N5, N0, N5, N1. We'll put it a 5 here. All right. So now we replace all of those from line 112 to line 121. Substitute the length of N5 to N1 with 5. All right, so that seems to work out. All right, so let's find out who is next. Basically, I'm looking at the comparison on the term on the right-hand side because that is the smaller one. All right, so we got N0, N1. All right, so N0, N1 has a value of 4. Hmm, I forgot to replace these. Okay, so this is 4. Okay, so these are the only two that I have not taken care of. Well, they're in on the path. All right. So now we got all the single edges or the single edges that go to a destination taken care of. So the next thing we need to do is to look at the ones that have multiple hops and replace those with, okay, let me repeat this one. So this is the length of N7, N3 plus the length from N3 to N8, which is a 3 that we have determined earlier. So now we can replace that with this. And basically we are just looking at everything that has N7, I mean N3, N8 and break those up. So like that. And this one too. And let's see, here's another one. And 2 more. All right. And we also have an edge from N6 to N8. So that means N6 to N8 is a 5. Like that. 6 to 8 is a 5. Like that. All right. And then N0 to N1 is a 4. So we can replace this one. And this one. All right. 2, 6 is not determined, right? 2, 6 is not determined. And then N7 to N2 is also not determined. Okay. All right. So now we have some more constraints to work out. So let's look for the one. Let's look for the one that we can resolve first. All right. So we see the N2, N6 All right, so now we can do some simplifications first. Okay, so let's do that. Um, so we get rid of this plus 4, subtract 4 from both sides, and this is now a 1. Subtract 3 from both sides, and now this is a 2. Subtract 3 from both sides, and this is now a 1. And let's see, we can subtract 4 from both sides. That's a 1. Subtract 3 from both sides, and that's a 2. Subtract 5 from both sides, and that's just greater than or equal to 0. Subtract 3 from both sides, whoops, and this is a plus 2. And subtract 3 from both sides again, and that is now a plus 2. There we go. All right, so that is much better. Because we just know all the distance of all the edges need to be greater than or equal to 0. So this is really not telling us anything, so we can remove that. This is also not useful, not useful, not useful, not useful, not useful. There we go. All right, so now we look at these constraints. Because the length of n7 to n3 has to be greater than or equal to 1, and it also has to be greater than or equal to 2, so this one is redundant. Greater than or equal to 2, greater than or equal to 2, so we only need one of them. And let's see. All right. All right, so it looks like n to n6 is going to be the next one, because n to n6 is only appearing on the right hand side. It does not appear on the left hand side, so it can be anything, because once we set it, we'll determine the length of the other edges. Okay, so we can pick anything for it. As usual, I'll pick a 3 just in case. So n2 n6 is now replaced with a 3. n2 n6. So here's n2, this is n6. We'll put a 3 over here. All right, so now everywhere we see that, okay, let me 106 to 103, replace the length of n2 to n6 with a constant of 3. There we go. All right, so now we can resolve some of these constants. 3 plus 1 is just 4, 3 plus 2 is just 5. Okay, and this one has a n2 n6 in it, so we can put it here, and then plus the distance of n2 n6, which is 3. So we get rid of that, simplify that to a 5, and I think that's the best we can do at this point. All right, so now we look for items that are only, or terms that are only appearing on the right hand side, and it looks like n7 n2 is the one. It only appears on the right hand side, so that means it is free to be anything we want it to be. So let's make that another 3. So n7 n2, n7 n2 is another 3. So going back to the graph, that's the 3 that I just added. Okay, so now we replace that. Okay, so we replace that to a 3, and then 3 plus 5 is an 8. Okay, so anything that's greater than 8 is automatically greater than or equal to 5. Don't need to mention that. Which is also anything greater than 8 is also greater than or equal to 2. So we can get rid of that. And that's it. Okay. So the next one we can determine is n7, n3. We know it has to be greater than 8, which means it can be 9. Oh, by the way, yeah, so it can be 9. So let's replace n7, n3 with a 9. So n7, n3 can be a 9. And then we go back here, and then we do the substitution. N7, N3 is a 9, and N7, N3 is a 9. Okay, so now this constraint is satisfied. We take it out, and then 9 plus 3 is a 12. All right, so at this point, we can simplify a little bit first. Anything that is greater than 12 is automatically greater than or equal to 3, so we can take that out. Anything that's greater than 4 is automatically greater than or equal to 1, so we can take that out. So now we are free to choose these two, the distance of these two edges. So n2, n1 only has to be greater than 4, so it can be 5. All right, so let's put it here. Oh, which one are we talking about? N2, n0. So n2, n0 can be 5. And then n7 and 8 can be 13. N7 and 8, n7 and 8 is going to be a 13 over here. All right, so this is supposed to work. So we will do a quick check, whether this works or not. And the way I can do this quick check is to do what we call a breadth first search. So the idea of a breadth first search is start with the destination and then work our way backwards to see which one is more promising. So we initially, let's see, I don't have a highlighter here, but I can use I'll use an asterisk to see which one is already considered. So the first one are these two. Okay, they have L values of 0. And then we expand, just one step beyond that. So we will have N7, N3, N6, N0, and N5 explored. So initially, the only path from N7 all the way to N8 has a distance of 13. And then now it gets tricky because now we have to actually prioritize based on the ones that has a star. In fact, I'm going to use a circle to mean these are taken out of queue. The ones with a star is in queue. The one with the star and a circle are not in queue anymore. And then the ones without a star is also not in queue. Okay. So out of all the ones with a star, we see the N3 is the next one. Okay. So we put a circle here. And then everything that goes into N3 will have a star. But since N7 already has a star, and N5 also has a star, so those two are okay. But we do have to add N2, into the set. So the first path that we find from N2 to a destination is N2 to N6 and then to N8, and it has a cost of 8. Okay, so I think we might run into a problem because we are supposed to find a shorter path from N2 to N0 to N1, but we'll see. Um, and I forgot about what I was about to do. Right, so N3 is the next is one. So now the ones with a star, which one has the least value? So N0 has the next least value. So we take it out of queue, and then we go to N2. But this time we did not find a shorter path. So N2 should not update to N2, N0, N1. And I'm not really sure whether I made a mistake here or not. We can look into how we update the L value of N2 because I might have made a mistake somewhere that's causing this to happen. All right, so let me just go back and check because I can look at the L value of N2 and see whether it got updated. All right, so the first time it got updated is here, which is normal, and it's going from N0. Yeah, I did make a mistake because I forgot. Yep, I made a mistake because I just didn't track my reasoning very closely. So it did find this path first, and it's, I'm fairly sure the values of the edges work out. It's just that, when I mentally track down Dijkstra's algorithm using a graph, that did not work out because the problem is I think I explored N6 before I explored N0, because N0 should be explored first because the L value of N0 is less than the L value of N6, which then would have found the longer path for N2 to get to N1, and then later on it would discover a shorter path from N2 to N6 to N8, which was what the trace suggested. So anyway, this is how I went in and determined the values of all of the edges. So we first figure out the topology, basically, where the edges are, which one goes to which one. And then we look at all the constraints and then try to look for things that only appear on the left hand side, on the right hand side. Um, I shouldn't say that. I should say, things that do not appear on the left hand side. So okay, so we look for things that do not appear on the left hand side implicitly or otherwise, and then we assign kind of random values to those particular items, simplify everything, and then repeat the process until we got everything figured out. All right, so this is the end of that explanation, and I'm gonna post this as soon as possible.